So we have it's like a work energy problem here with a ring rolling up a ramp. So let's get a diagram going here. So we have a 22-degree angle, and we've got this ring, the base of the ramp, moving with some initial velocity v0 up the ramp. It's going to travel a length L up the ramp, and it's going to go up a height h is equal to L sine 22. Right? So to solve this with work energy, which I think would be the easiest here, we can identify the forces acting on the ring, which is gravity and the normal force. Let's see, so the work done by the normal force is 0 during the motion. Work done by gravity is always takes on the form of mgh. In this case, it's minus mgh because it goes up. So that's minus mg times L sine 22. Alright, so let's keep that aside for now. And so the next step is to use the work energy theorem, which says the sum of the works done by all the forces is equal to the change in kinetic energy. So this is 0 minus mg L sine 22 is equal to the change in kinetic energy, kf minus ki. Now kf is 0 at maximum height, right? We're asking how far up the ramp does the sphere or the ring roll until it stops, and that's like a max height problem. So the final kinetic energy is 0. So we have minus mgl sine 22 is equal to minus the initial kinetic energy. So let's write out what the initial kinetic energy is. It's 1/2 mv squared, so the translational kinetic energy, plus 1/2 I omega squared. Oh wait, v naught omega naught. I'm going to go ahead and distribute this minus sign. So it's minus 1/2 m v naught squared minus 1/2 I omega naught squared. And now let me make my substitutions. I know that for a ring, I is equal to mr squared. And I also know that since it's rolling without slipping, that omega naught is equal to v naught over r. So omega naught squared is v naught squared over r squared. So this becomes minus 1/2 m v naught squared minus 1/2 mr squared times v naught squared over r squared. Okay, so this becomes minus 1/2 m v naught squared minus 1/2 m v naught squared. So I'm left with minus mg L sine 22 is equal to minus m v naught squared. And the m cancels. And I'm left with, if I solve for L, I get L is equal to v naught squared over g sine 22, which is 8.2 meters. Right, as usual with the work energy theorem, we're left with a single unknown. Right, because the initial velocity was 5.5 meters per second. I guess I never wrote that down anywhere. Notice what it doesn't depend on, by the way. The radius of the ring doesn't appear in this equation. The height only depends on the fact that it is a ring, so that it's moment of inertia mr squared, and it depends on the initial velocity, but it does not depend on r specifically. Okay, so we've done part A. Let's do part B. Part B says if we rolled up a sphere with the same initial speed, what would happen? Well, let's compare the ring's kinetic energy, which is the initial kinetic energy is m v naught squared. Let's compare that to a sphere's initial kinetic energy, okay, which is 1/2 m v naught squared plus 1/2 I omega naught squared. Now for a sphere, I is 2/5 mr squared. Now the sphere, like the ring, we're going to assume is rolling without slipping, so this becomes 1/2 m v naught squared plus 1/2 times 2/5 mr squared times v naught squared over r squared, making my substitutions. So this becomes 1/2 m v naught squared plus 2/10 m v naught squared, or 7/10 mv naught squared. Now, if I compare the ring's kinetic energy to the sphere's initial kinetic energy, it's clear that the ring has more kinetic energy. So, so the ring has more initial kinetic energy, and so it goes further up the ramp. Right, because gravity can do more work, I guess, on the ring. Okay?